Thank you. And thanks the organizers for the invitation. I am enjoying my time in Lumini. Now the result I would like to describe was inspired by a talk that some of us attended 3 weeks ago in Oberwolfach. Right? In a very nice talk, Dodson-Luhrmann presented his joint work with Ben Dodson and Dana Mendelson on almost sure scattering for the energy-critical wave equation in 4 dimensions with radial data. After his talk, I asked him what about the analogous result for the Schrödinger equation. He indicated there are some issues, so we decided to give it a try. Okay, so the result that I'm going to present is really the analog of the result, but the energy-critical wave equation is replaced by the energy-critical Schrödinger equation. Okay. All right, now there is a very rich history of well-Poisson's results for dispersive equations with randomized initial data belonging to supercritical spaces, and I'm certainly not the best person in the room to give an overview of such results. There are persons present here that have worked extensively on this topic, and they would do a much better job than me. In fact, I would like to thank Hiro for doing partly that on Monday. Okay, so instead, I am going to focus on the energy-critical problem in Euclidean space. Okay, so all the results that I'm going to mention have the following thing in common. They take initial data F in the Sobolev space HS, okay, for some S strictly less than 1, okay, and then they randomize it in a way that I'm going to explain shortly. Okay, now for that sort of random data, there are 2 types of results. We have almost sure global well-Poisson's was first proved for the energy-critical wave by Wana Pokovniku in dimensions 4 and 5, and then in joint work with Hiro, Wana established the result in dimension 3. Okay? For the energy-critical NLS, the almost sure well-Poisson's result for 4 dimensions is due to Beni, O, and Pokovniku in dimension 4, and by Brereton in dimension 3. Okay, and I should mention that these 2 results over here are conditional on scaling critical bounds for the difference between the nonlinear solution with randomized initial data and the linear evolution of the randomized data. Okay, so they are conditional results. Now, all these results establish construct solutions that are global in time almost surely, but they do not tell us information about the almost sure asymptotic behavior of solutions. Right? The only result in that direction that I'm aware of is the one that I just mentioned. Okay, so almost sure scattering for the energy-critical wave equation due to Dodson-Luhrmann and Mendelson in 4 dimensions for radial data. Okay, and the result that I would like to present is really the analog of the result here, but for the energy-critical Schrödinger equation. Okay. All right, so in what follows, I'm going to move this all the way up. I don't think I budgeted time for moving the board. Okay. All right. So in what follows, I'm going to consider the following equation. I times the partial derivative of u with respect to time plus the Laplacian of u is equal to u squared times u. Time takes values in R, and space is 4-dimensional. Okay? Nowadays, we know quite a few facts about this equation, and let me tell you briefly in 2 or 3 minutes some of the facts that matter to us. So solutions to this equation conserve the energy. The energy is given by the kinetic energy, half the gradient of u squared, plus the potential energy, which is the L4 norm of u. Okay? And solutions to this equation also enjoy a scaling symmetry. Okay, so the map that takes u to this rescaled function of u, 1 over lambda u of t over lambda squared x over lambda, leaves the class of solutions invariant, right? It maps one solution to another solution. This scaling also leaves invariant the energy, so the energy of u lambda is the same thing as the energy of u, which is the reason why this equation is known as energy critical. Okay? So nowadays we know that this energy critical equation is well posed in the energy space, and we rely on that theorem. So let me state it for you here. So theorem. This is joint work with Rickman in 2004 when I was a graduate student, and it says the following thing. Let U naught be in the energy space, right? So we see that the space H1 dot really is the energy space. The H1 dot norm is the kinetic energy norm, and the potential energy is controlled by Sobolev embedding by the kinetic energy norm. Okay, so this is the energy space. Then there exists a unique global solution, U to NLS, with data at time 0, let's say, being given by the initial state U naught. Moreover, the solution enjoys uniform space-time bounds. So, for example, the L6 norm is controlled globally in time, okay? And it's controlled by a function that depends only on the energy of the initial data. Now, as a consequence of those space-time bounds, we know that the solution scatters, okay? So in particular, there exist scattering states, U plus minus, in the energy space, such that the solution U at time t looks asymptotically like the evolution of those scattering states in the energy space. And as I said, asymptotically in the future and in the past. Okay? So the proof of this theorem really follows the arguments of Bourgain and the I-team introduced in order to solve the energy critical problem in 3 dimensions and incorporate some simplifications which are made possible by the fact that the dispersion in 4 dimensions is better than the dispersion in 3 dimensions. So we know that the equation is well posed in the energy space. We also know that it's ill posed in supercritical spaces. Okay, by work of Chris, Leander, and Tao, who proved that the data to solution map fails to be continuous at the origin in the HS topology if S is strictly less than 1. Okay? However, we believe that generically this equation is well posed even for supercritical data. So that brings me to explaining to you what sort of data we consider. Okay, so let me explain to you what data we consider. Okay, so like the people before us, we have to take everyone's favorite bump function, phi, C infinity with compact support, inside the unit ball, radial, okay? And such that if you take this function and you translate it to every single point in the lattice in R4, then you get a partition of unity, okay? And such that the sum over all the points in the lattice of phi of xc minus k is 1 for every single xc in R4, okay? Now, to save time in the future, I am going to denote by phi k the translation of phi at the lattice point k, okay? All right. Now, given a regularity index S and a function f in Hs, okay, and a lattice point k, we define fk via what happens on the Fourier side. So on the Fourier side, you simply take the Fourier transform of f and you localize it around the lattice point k. So you multiply it by this bump that lives around k. Okay? So on the physical side, it's clearly the inverse Fourier transform of that. Okay? So this is just phi k check convolved with f. Okay? Now, here's our randomization. We're going to take xk to be independent mean zero, complex valued, Gaussian random variables, and we define our normalization. So sorry, our randomization f omega to be the sum over all the points in the lattice of xk of omega times fk. Okay? So a few remarks about this randomization. So remarks that should be immediately clear to you. First of all, if f is in Hs, then f omega is in Hs almost surely. Okay? And it's not going to live in any higher regularity space, which is very easy to see just by looking on the Fourier side. Okay? Now, the second thing I would like to remark is the following, right? We're going to prove a theorem for radial data. Okay? However, even if you take f to be radial, so even if f is radial, f omega is not. Okay? In order for a function to be radial, its Fourier transform should be radial. But if you look at the Fourier transform of this randomization, what is it? It's the Fourier transform of f, okay, which is multiplied by these random height bumps at every single point in the lattice, right? So it's very non-radial. Okay? All right, now f omega is clearly a Gaussian process, so let's compute its variance at a point. Okay? So I'm going to write it here. Here is a lemma, a variance bound, or estimate if you want. The expectation of f omega squared at a point x is bounded by the absolute value of psi check convolved with f squared at the point x. Okay? So besides allowing us to better understand our randomization, we are actually going to rely on this bound in our proof as well. Okay? Now, as you will see, this from the proof, okay, this inequality over here is pretty sharp. Okay, so in particular, there is no reason to expect that the randomization is going to decay any better than the function you start with. After all, a convolution decays only as fast as the slowest decaying function. Okay, so let me present to you the very simple proof. Okay, how would you prove something like this, right? We have to compute the variance of f omega at a point. So what can you possibly do? You're going to use the definition of the randomization. You write it twice because you have a square over here. You open up the parentheses. And using the fact that you're dealing with independent mean zero Gaussian random variables, it's very easy to see that this is basically the sum of fk squared evaluated at the point x. Okay? But now what is fk? It's just the convolution of f with psi check k. So this is like the sum in k. I am going to write two integrals, one for every single fk. So what do I have here? I have psi check k at y, f of x minus y, psi k check at z, f of x minus z, dy, dz, and I need a bar over the last terms. Okay? All right, but psi k is just a translation of, phi k is just a translation of phi by this lattice point k, and the Fourier transform turns translation into a multiplication by a character. So this is nothing else, but this, let me put the sum inside, it's nothing else but double integral, the sum over all the lattice points, e to the I k y minus z, psi check of y, psi check of z bar, f of x minus y, f of x minus z bar, dy, dz. All right? But now, by Poisson's summation, a sum of character is the same thing as a sum of delta functions, right? So this is the sum over L in Z4, the delta function of y minus z minus L. Okay? So now let's integrate one of these variables, let's say z. So I get that this is the same thing as move the sum back outside, the sum in L, the integral in y, psi check of y, psi check of y minus L, bar, f of x minus y, f of x minus y plus L bar dy. Okay? And here is the very first inequality that I'm going to use in this computation is the arithmetic geometric mean inequality. So the parenthesis over here is bounded by psi check of y, psi check of z into f of x minus y squared plus f of x minus y plus L squared. Okay? So let's focus on this. So all I wrote was an inequality for the integrand. Okay? So let's focus on the first term over here. Okay? Oh, sorry, z is y minus L. All right. Now, because phi was infinity with compact support, its inverse Fourier transform decays arbitrarily fast. So using the rapid decay over here, we can sum in L. Okay, so what are we left with? We're left exactly with the convolution between psi check and f squared. Agree? So this is bounded by the convolution between psi check and f squared evaluated at x. Okay, so that's the first term. What about the second term over here? Well, first you can do a change of variables to replace x minus y plus L by x minus y. Then this y minus L becomes a y, but this creature over here becomes a y plus L. So using again the rapid decay of psi check, you can sum in L using this bound over here, right? So what you get is again the convolution of psi check with f squared. Okay, so it's a very simple lemma that gives us a various bound on of f omega. Now, in particular, right, why is this so useful? Once you have a variance bound, you can get a bound on all higher moments. Okay, so if you want the expectation of f omega to the power 2m evaluated at x is bounded by a constant that will depend on m, psi check involved with f squared evaluated at x to the power m, okay, for every single m big or equal to 1, for example. Okay, and once you have this, we can compute the expectation of the L to M norm in X of this randomized data. Okay, so how would you estimate something like this? Well, you can use Fubini to interchange the integral in X with the expectation. Use this bound on the higher moment. So you see that this is bounded by psi check convolved with f squared in Lm to the power m. Okay? So now what do I do? Well, I'm simply going to put f squared in L1 and I'm going to put psi check in Lm. Okay? So you immediately see that this is bounded by f in L2 to the power 2m. Okay? So while our randomization is not smoothing in the sense that it's going to land you in a higher Sobolev space, it is smoothing in this sense. If you simply start with an initial data that is in L2, the randomization is going to lie in all higher Lebesgue spaces. Okay? All right. So that's all that I really wanted to tell you about this randomization. Now we understand that a little bit better, we can state the theorem. Sorry. All right. Now let's get this one down. Okay. So here is the theorem. This is joint work with Rowan Killip and Jason Murphy. And it says the following thing. Let's fix S to be between 5, 6, and 1. And let's fix F in H's of R4. Then, for almost every omega, there exists a unique global solution U to NLS with initial data U at time 0 being F omega. Okay? And moreover, the solution scatters in the following way. So there exist asymptotic states V plus minus in the energy space, okay, such that if I subtract from the nonlinear solution the free evolution of the randomized data, okay, what is left over scatters in H1. Okay, so it scatters to the asymptotic states V plus minus in the energy space as t goes to plus and minus infinity. Okay? Oh, and I forgot to say radial. Major assumption, okay? Radial. All right. So for the remaining time, I would like to sketch the proof of this result, okay? So sketch of proof. So how would you prove something like this? Well, you want scattering for this difference over here, so we're simply going to write the nonlinear solution U at time t as the linear evolution of this asymptotic, of this randomized data, plus whatever is left over, let's call it V. Okay? And so that I write a little bit less in the future, I'm going to call this linear evolution capital F omega, and V is V. Okay? So now let's look at the equation that V satisfies. Okay, so what is the equation that V satisfies? I times the partial derivative with respect to time of V plus the Laplacian of V is equal to this forcing term F omega plus V squared into F omega plus V. Okay? And the key is to think about this forcing term as a perturbation of the energy critical nonlinearity. Okay, so you think of it as the energy critical nonlinearity plus an error. Okay, and the error is obviously this one. Okay, so this is the error of V in satisfying the energy critical nonlinear, energy critical equation. Okay, so what do you do from here? Let's see, can we do it? No. One button at a time. You can't use two buttons. Okay. Okay. So now what is the idea? The idea is to use the stability theory for the energy critical NLS. Okay? So the stability theory for the energy critical NLS is going to allow us to conclude that V is global and scatters in H1, right, in the energy space, provided two conditions are satisfied. The first condition is that the V is uniformly bounded in the energy space. Okay? So V in L infinity in time H1 dot in space is uniformly bounded on its lifespan. Okay? And the second condition is that this error of V in satisfying the energy critical equation is small in suitable spaces. Okay? What are suitable spaces? Well, critical scaling dual Strickland spaces. Okay? Now, the stability theory for the energy critical NLS was developed by Bourgain and the I-team and used in their proof of well-posedness in the energy critical space. The utility of the stability theory for NLS to perturb the equations was first observed by Xiaoyi Zhang, and then it was elaborated on in a joint work with Terry Tao and Xiaoyi when we considered Schrödinger equation with combined power time nonlinearities. And the usefulness of this stability theory for NLS in the random setting was first exploited by Pokovnikova in her proof of almost well-posedness for the energy critical wave equation. Okay? All right, so in what follows, all I have to convince you of is that these two conditions over here are satisfied, because then the stability theory simply solves the problem for me. Okay? And I'm only going to focus on this point over here, uniform energy bounds for V, because it turns out that once you understand that, the sort of tools and inequalities that you use in order to establish this also show you that the error is small in all the right spaces. Okay? So the only thing that you really need to understand is this uniform energy bound for V. Okay? So, how are we going to achieve that? All right. So let E of V of t denote the energy of V. Okay, so it's half of the gradient of V of t squared plus a quarter V of t to the power 4. Now, because V is not a solution to the energy critical NLS, it solves this up to an error, this energy over here is not conserved, okay? So we have to estimate its increment, okay? And again, so that I write a little bit less in the future, let E of capital T be the supremum of this energy up to time capital T. Okay? Now, in their work, Wanan and Hiro were able to obtain bounds on this quantity over here that grow in capital T. Now, if all you want to do is prove almost show global opposedness, that is good enough, right? But if you want to prove scattering, then you really need to control this quantity uniformly in capital T, okay? So let me show you how we do that. So how do we do that? You have to take a time derivative of the energy, okay, in order to control its increment. So what do you get? Well, a direct computation tells you that this is minus the real part of Vt bar into the error of V satisfying the energy critical NLS. Okay? Now, if you're dealing with the energy critical wave equation, you could use Cauchy-Schwarz, take this guy out here in L2, because the energy controls the L2 norm of the derivative of V, and then you're left estimating this creature in L2. We're dealing with the Schrödinger equation, right? So we really know nothing about the time derivative of V. So like Wana and Hiro before us, we integrate by parts in time, okay? So integrate in time. by parts, integrate by parts in t, we get the following thing. Let me move, which one is this one? Move it a little bit high. We get something like this. The energy of V at time t is bounded by the energy of V at time 0 plus boundary terms obtained from the integration by parts in t, plus what happens when you move the time derivative from here to here. Now you can arrange such that the time derivative always finds the evolution of the randomized data, so you get something like this. The time derivative of f omega into, well, the worst term that you're ever going to have to face is v cube, right? 2 copies of v coming from the parentheses and 1 more copy coming from here, okay? So it's this creature plus easier terms, okay? Now, because f omega is a free evolution, the time derivative is the same thing as the Laplacian of f omega, right? So integrate by parts in space, you can bound this by the gradient of f omega. The gradient is going to attack one of the 3 copies, and then v squared in L1 of spacetime, okay? So all that I really need to do is convince you that we can obtain uniform in time bounds on the boundary terms over here and this term over here in order to control the energy increment uniformly in time, okay? So let's see, how do we do that? All right, so this one is going to move all the way up. All right, so I will start with the boundary terms and try to explain to you how to get uniform bounds. So the boundary terms look like this. They are of the form f omega times 3 copies of v, which you have to estimate uniformly in time, L1 in space, okay? So how are you going to bound something like this? Well, you're going to use the energy, take 3 copies of v and throw them into the energy space, which is the potential energy, and then you have f omega in L infinity in time, L4 in space, okay? So this creature over here is bounded by E capital T to the 3/4. So in order to get our uniform control, I simply have to control the L4 norm of f omega uniformly in time. Okay, so how do you do that? It's easy to get a bound that grows in time. How do you get a bound that is uniform in time? Well, I'm going to do something very, very easy. I'm just going to apply the fundamental theorem of calculus, okay? So I'm going to write f omega at a time t to be f omega at some time t naught plus the integral from t naught to capital T, the time derivative of f omega s ds. Okay, fundamental theorem of calculus. Now I take this relation over here and I localize it on a frequency annulus of radius n. Okay, so simply localize in frequency. All right? So now what do I have to do? I have to control the L4 norm in space. So by the triangle inequality, this is bounded by the L4 norm of this guy plus the L4 norm of this guy. Okay? So now, if I want to control the supremum of the L4 norm on a time interval I, given that this time t naught over here can be taken to be arbitrarily belonging to that interval I can bound the contribution of this guy by the average of the L4 norm on the interval I. Okay? So, f omega n in L infinity in time, L4 in space on a compact time interval I is bounded by the average of Fn omega on the interval I, plus the contribution of this term over here, which is bounded by the time derivative of Fn omega in L1 in time, L4 in space. Okay? So what do you do now? Well, I want to move from this space over here to a symmetric space-time norm. So I'm simply going to do Hölder's inequality in time. Okay? So I'm going to continue. This is bounded by, when you do Hölder in time, you get the length of I to the power 3/4. So I'm going to get I to the minus 1/4 plus, what do I get from here? Well, I get I to the power 3/4 times what? Well, F omega is a linear evolution, so the time derivative is the same thing as the Laplacian. And because we are localized to frequency n, the Laplacian is like n squared. So times n squared. F omega n in L4 space-time on I cross R4. Okay? So what do we do now? We're simply going to tile the real line by intervals I. So tile the real line by intervals I of length, let's say delta. Okay? Once you have done that, you can raise this relation to the power 4 and sum in the intervals I. Okay, so what do you get? You get that Fn omega in L infinity in time, L4 in space, over the whole space-time is bounded by delta to the minus 1 plus delta cube n to the power 8 Fn omega in L4 space-time to the power 4. Okay? So what do I do next? I'm simply going to take the expectation of this relation. Okay? But by the variance bound that we just proved, you can prove that the expectation of the L4 norm in space-time is bounded by Fn in L2 to the power 4. Right? It's a very easy application of this bound over here. Okay, so what do I do now? Well, I'm simply going to take delta inverse to be like n to the power 4s, okay? And then all that I need to require is that the delta cube times n to the power 8 is also bounded by n to the power 4s, which a quick computation tells you is true as long as s is bigger than the power 1/2, right? So in that case, you see that this expectation over here is bounded by Fn in hs to the power 4 for every single s bigger than 1/2. All right? All right, so we were able to control almost surely the L4 norm, the supremum in time of the L4 norm of Fn omega in terms of this, simply sum in all the frequencies n, right? In order to see that the boundary terms are bounded by the function f in hs as long as s is bigger than 1/2. Our theorem really requires that s is bigger than 5/6, so this is certainly acceptable. Okay? All right. So what now? Let's turn to the hardest term, right? That term over there. So we are left to estimate the gradient of f omega times the gradient of v squared in L1 space-time, okay, uniformly in time. So how are we going to do this? Well, take one. You might be tempted to simply put every single copy of v into the energy space. So what would you get? You get something like this. The gradient of f omega, the gradient of v times v squared in L1 space-time is bounded by, throw the gradient in L infinity L2, throw every single copy of v in the energy space, so that's L infinity L4, and then you're left with estimating the gradient of f omega in L1 in time, L infinity in space. Okay? Now, the first thing I want to convince you of is that it is impossible to control this term over here. Okay, cannot control it. So why not? Well, here is a specific example. Take psi to be your favorite bump function, supported inside a unit ball, say away from the origin to make some computations easier, and define f hat to be a sum over all n's big or equal to 0, Cn e to the I xc squared n factorial, let's say, times psi of xc. Okay? And I'm going to take this coefficient Cn over here to belong to little L2. Okay? Now you see that the randomization does absolutely nothing to this function, right? Because it is supported in the unit ball. All it does is multiplies it by a random number. Okay? Now, however, because we put this rapid oscillation over here, these waves are almost orthogonal. So it's very easy to see that f in L2, okay, is bounded by these coefficients in little L2. Okay, it's a very easy computation. Now, what happens to the linear evolution of this function? Well, the linear evolution looks like this. It's going to be a sum of linear evolutions that are translated in time by n factorial. Agree? So at every single time n factorial, we have refocusing, right? So e to the I n factorial Laplacian applied to f, if I want to measure this in L infinity, this is basically going to be like Cn, right? Because all the other wave packets have dispersed by the time n factorial. Okay? So now take L1 in time of this guy, you just get the little L1 norm of the Cn's, right? And I need to replace this by the t. And this is clearly infinity. Okay? Because you can take your Cn to be in L2, in little L2, but not in L1. So this argument over here tells you that you have no chance of controlling a term like this unless you're willing to replace the L1 by at least L2 in time. Agreed? Okay? So how are we going to gain integrability, right? We need additional time integrability on V. So what do? We use the idea of Dodson and Luhrmann and Mendelson. And down. Okay, we're going to use the motorways inequality. So take 2, use motorways. So what does motorways say? It tells us that the space-time integral of v to the 4 divided by x dx dt is bounded by e of capital T to the power a half plus errors resulting from the fact that v does not solve the energy-critical NLS, but it solves it up to an error. Okay? So let's ignore these errors over here for now. And let's see how would that help us control that term over there. So you could argue like follows. You can take the gradient of V and you throw it again in the energy space. You take V divided by x to the power a quarter and you throw it in L4 space-time, okay, because this is what Moravec controls. And then you're left with x to the power a half, the gradient of f omega, in L2 in time, L infinity in space. Okay? So we're able to replace that L1 exponent by L2. So this argument over here is no longer a counterexample. Okay? So let's see, do we have a chance of controlling this guy over here? So how would you bound something like this? Well, assuming for a second that f omega over here is radial, it is not, but let us assume it is, one can use weighted radial Strickard's inequalities. Okay, so here is an example that we could prove. So weighted radial Strickard's. says the following thing. You take x to the power 2 times q minus 1 divided by q, the free evolution of f. You measure it in LQ in time and infinity in space. This is bounded by f in L2 for every function f which is radial, and for every q strictly bigger than 2 and smaller or equal than 4. Okay? So the problem that we face over here is that this space, okay, in which we need to measure our randomized free evolution is not covered by the weighted radial Strickland's inequality that we have, right? Because q is not allowed to be 2 in this inequality that we have over here. Okay? And not only would we need an endpoint over here, but we also need a little bit of wiggle room because we need to eat some of the derivatives that hit the free evolution, right? Because we want a theorem for an s strictly less than 1. Okay? So, however, let me just point out one thing. For all its faults, okay, this inequality over here does have enough powers of x, right? If you take q to be 2, I know I told you you shouldn't, but let's take it for a second. If you take q to be 2, you see that this power over here is 1, and we only need to eat an x to the power a half, okay? So what do? We need to increase this exponent of here even more. So the only way we can go is lowering the L infinity on the gradient. So how can you do that? Well, take 3, add convexity to the motorways. Okay, so take 3, and our last piece of the puzzle. So let m of capital T be the integral from 0 to capital T, the integral over R4, v to the power 4 as before, but I replace the absolute x by Japanese x by adding this convexity. I am able to gain integrability of the gradient provided I pay this huge weight. Okay? So this is bounded by, again, e of t to the power half plus errors. Okay? So how does this help? Okay, let's ignore the errors again. So how does that help? Well, it allows you to control the gradient in LP in time, L2 in space for a p strictly less than infinity, provided that you pay a weight like 3 divided by p, right? This is controlled by the motorways to the power 1 over p and the energy to the power a half minus 1 over p, right? Simply by interpolation. Okay? So what? Well, how does that inform our bounding of that term? I have to estimate this one in L1 in space-time. So now I take the gradient of v divided by x to the 3p. I throw it in LP, L2. I take v and I divide it by Japanese x, and I put it in L4, 2/4. And then I'm left with x to the power 3 over p plus a half, the gradient of f omega, and now an exponent which is strictly bigger than 2 in time, L infinity in space. Okay? So, one more minute, maybe 2. All that I have to tell you is that one can control this term over here uniformly in time, right? If I can show you that, then it's pretty clear that we were able to control the energy increment in terms of the motorways inequality. Now, it turns out that if you can control this term over here, you can also control the errors present in the motorways inequality. So you can also control the motorways quantity in terms of the energy increment. Okay? So it all hinges on this term. Control of this term means that you can control the energy increment in terms of the motorways, and the motorways in terms of the energy increment. Right? So running a double bootstrap argument, one can obtain uniform bounds on both the energy increment and the motorways. Okay? Provided you can control this term. Okay? So now let me briefly, right, I'm running out of time, so let's just me tell you what are the tools that go into controlling this term over here. So we use 3 things. So to control this term, we use the variance estimate that I showed you and I just erased. Okay, so variance estimate. How does that enter? Well, by Sobolev embedding, I can replace this L infinity over here by a large Lebesgue space simply by taking an epsilon number of derivatives. But now that I have replaced this guy by an LP or an LQ or LM, okay, for an M which is not infinity, I can use the variance estimate, okay, which allows me to replace the evolution of the randomized data by the evolution of the actual data, which is radial. Okay, so now that you have the evolution of a radial function, you can use the weighted radial Strickard's inequality to eat these weights. Okay, so use weighted radial Strickard's to eat the weights and use local smoothing to eat derivatives. Okay. So the local smoothing looks like this: e to the it Laplacian f divided by x to the power a half plus epsilon, any epsilon in L2 spacetime is bounded by negative derivative, half a derivative of f in L2. Okay? So you're actually going to interpolate between the weighted radial Strickard's and the local smoothing and able to control this term over here by f in hs for s bigger than 5,6. Provided that you take your p to be sufficiently large. Okay? So again, controlling this term over here allows you to do a double bootstrap argument to control both the energy and the motorways inequality uniformly in time, right? And that's all you have to do, because then the stability theory takes care of everything else. Okay? That's it. Thank you.
Okay, thank you. So are there any questions, comments or remarks?
I wanted to know how do you get this estimate of Fn omega, the center of this estimate? Capital Fn omega in L4, you say it's you estimate it by small fn in L2 related to the variance estimate you did. But how do you get the L4 in time? I don't see it.
So the key is to use the variance estimate to travel from the L4 in space to a space that is controlled by the Strickard's inequality.
Okay.
Okay, so the variance allows you to put a psi check in L4 thirds or something, which means that you just have the free evolution in L4, L8 thirds, I think, is the Strickard space. Right? And then the Strickard's inequality simply gives you L2.
So this is Strickard's.
Yeah, it's very easy.
Other questions? No? Okay, let's thank the speaker again.